Yeah, counts on everyone. Let's start off. Great, last thing that we did, we are seeing all these things moving around. Great, let's see one more before going ahead. So we got a wedge here. Let's say this is capital M, this is also capital M, and this is theta, and all surfaces are smooth. Find acceleration of the wedge. Others do keep your cams on. G tan. Okay. Nee, how did you get that? Did you assume the ball is falling down with G? If the ball is falling down with G, freely falling, then it would be G tan theta. That means you assume there is no other force on the ball other than mg. Even the 30-40 seconds, and then we'll see. Okay, let's see. How can you get G by 2 when there is a theta there, meaning your answer is independent of theta? Step one, choose your system, draw the free body diagram. The story is always the same. You follow the process. Normal reaction. N ground. Your own weight mg. Bus, there are only three forces. On the sphere. N. N wall, your own weight mg. Perfect. Accelerations, let this be a1, let this be a2. Right? This we have done in constraints. If here this is going with a1 and this here is going with a2, acceleration along the normal must be same. If this is theta, this is 90 minus theta, this is 90 minus theta, and this is theta. So this component would be a1 sine theta. This component will be a2 cos theta. So we get a1 sine theta is equal to a2 cos theta. This was the relation between the accelerations. Hmm. Hmm. Yeah. And this we derived in constraints, if you remember. Which one? This guy. The first part of the problem. VB is u tan theta. Means if the wedge is going with u, B will come down with u tan theta. Great. And what are these angles there? So we just now saw these angles. This angle was theta. So this component will be in sine theta. This will be in cos theta. This would be in cos theta, and this would be your in sine theta. FBD equations and constraints. Now, this guy is only moving in the horizontal direction. The only guy pushing is n sine theta. N sine theta is MA1. This thing, the only thing which is pushing down is mg. So this is mg minus n cos theta is mass into acceleration a2. Take n from here, which is ma1. But what is a1? A1 is a2 tan cot theta by sine theta. Take this and substitute here. I'm trying to find a1, right? Okay. Then this will be mg minus n will be ma2 cos by sine, that will become cot square theta is equal to ma2. We get a2 is equal to g by 1 plus cot square theta, which is cosecant square theta. So that will be g sine square theta. That's your a2. Then your a1 will be a2 g sine square theta cos theta by sine theta. One sine will go off, you end up with g by 2 sine 2 theta. Check your answers. Not sure how you guys got an answer without theta. Because you can clearly see, if this question comes in the exam, I will kind of guess like this. If you put theta is equal to 90, how will the picture be? The wedge will become like this, right? Like a block. Then what will happen? The ball will fall down with g, isn't it? Suppose you put theta is equal to 0, this will become a flat surface. Then the ball will have acceleration 0. So could have guessed it if they asked you the acceleration of the ball. But please say where it went wrong. The free body diagram, the constraint equations, resolving forces, component and solving. The process is still the same. Let them give any problem. This is the process. Something changes, you know way to do the adjustments. All clear with this? Yeah. Next time. Find the acceleration of the blocks. Pulleys are movable. Let's see these kind of problems, right? There's a small catch there. If you look at that string, the whole thing, the string is same. This actually creates a problem. If you just look at this pulley here, if you say this is tension T, this is tension T, this is tension T, and this is the same string, and this is also tension T. So if you look at this pulley here, I'll just call this guy A. This is tension, and this is tension. So 2T minus T is mass of the pulley into acceleration of the pulley. And mass of the pulley is zero. Therefore, the tension is zero. There is no tension in the string. All the strings are loose, right? So both the blocks fall with G. So at that instant, so the whole string becomes loose and the whole thing just falls with G. It's a free fall. There is nothing to stop them. Clear with this? Yeah, I know it's difficult to make something like that, but when you leave it like this, the whole string becomes literally loose. So this thing doesn't work. Everything is falling with G. That's the whole idea there. Clear? Next thing, let's see whether this thing is loaded or not. This is not loaded, but I think we can do this question. This is a good one. We should have done this in catenary. Let's get this. Let's give an answer on this. Can you keep your cam on? Okay. B, anyone else? I'll give another 30, 40 seconds. Okay, let's see. Read the question. The uniform chain of mass 10 kg, length 10 meter is hanging. So basically 1 kg is 1 meter. Vertical part is 3 meter. So this part is 3 meter. This part is 3 meter. Find the tension at the midpoint of the string A and the pulleys. Now, a few things you have to be careful here. These strings are at an angle. So there is some theta here. And he's saying neglect the length of the string on the pulley. So we can ignore that. So here, if I take the tension to be some T1, and this weight will be 3 kg, so that will be 30 newtons because that is 3 meters. So T1 is 30 newtons. So tension here also will act T1 at an angle. So here also tension is acting T1 at an angle. And if I just look at this half part here, at this point, the tension will be TA horizontal. Now, if this is 3 meter and this is 3 meter, that means the remaining balance is 2 meters. So this weight must be 20 newtons. I'll just draw that half ka thing there. So this half which is looking like this. So we have a T1 here with an angle theta here, and we have TA here, and we have our own weight 20 newtons here. Perfect. So T1 cos theta is balancing the 20 newtons, and T1 sine theta is balancing your TA. Square them and add them, then you'll end up with T1 square is equal to 20 square plus TA square. And what is T1? T1 is 30. So TA square is 30 square minus 20 square. That's 500. So TA is 10 root 5. Is that making sense, everyone? So you take the FBD of the right half or the left half of the string. Right, Ananya. All clear with this? Yeah. So good one. Not really that tough, but should know like this is 3 kg, this is 2 kg, 2 kg, and 3 kg. So it's all distributed there. Next thing. All clear? Any doubts on this? Next thing, weighing machines. What does a weighing machine actually measure? What does a weighing machine measure? Don't get confused between what it measures and what it shows. The weighing machine does not measure mass. It does not know what is your mass, right? If you take your college ka bag and stand on it, can it tell the difference between you and the bag? So what is it measuring here? So if you take your weighing machine and go to moon, you won't get your mass. So it actually measures normal reaction. And then you calibrate it. So the word is that we call it calibration. So this is what happens. Most of the equipment, right? They don't actually, show you what they're measuring. So what I show you and what I measure are two different things. It shows the reading. It shows reading which is normal by acceleration due to gravity. So it doesn't measure your mass. It measures normal reaction, but it shows normal by G. G is your Earth ka G. So they assume like, oh, that is your mass. Getting it? So this is called calibration. So I still remember in my first year of IIT, right? First semester, we had a project. So we had a course called engineering design. So, right? In the first semester, you study physics, chemistry, maths again. In case you don't know, IIT first semester, you again study physics, chemistry, maths, right? And our bad luck, IIT Madras, we even had biology also, which came under engineering design course. And their idea was biological design is also a design. So it was some weird course. It used to be in the afternoon 2 to 3:30 after heavy lunch. Hopeless time. So it's a good time to sleep actually. So anyway, so the codes, right? They used to come every 3 weeks. Some new guy used to come in. They used to teach something about design in different things. One guy talked about robots. One guy talked about DNA ka structure ka design. It was a mix and match of the course, but so in that, right, we got a project. Our end semester ka project, right? Exam was 50 marks, and there was you had to make a prototype. They gave 3 projects you can choose from. I don't remember the remaining 2, but my project was anemometer. It's a device to measure wind speed. Simple thing. So the conditions are this: you have to form a team of 3. All 3 must be from different branches. So I and another 2 friends are there. So I was electrical. There was one guy from mechanical, one guy from chemical. So college ka friends. So we formed a group. And the idea was we got 1 week time to make it. So what we did, as usual, lazy people, we really didn't think much. So we made the most standard one. If you ever been to any railway station, metros or airports, right, you will see this design. You have cup kind of things, like something of this sort. When the wind blows, this thing rotates. So based on the rotation, you can figure out the speed kind of thing. So we took that design. Now the problem is, how do I connect this rotation to the speed of the wind? So what we did, we connected this to an axle. We connected this to a dynamo. So whenever this thing rotates, we are getting voltage here. So we wanted to relate the voltage to the wind speed. So this device measures wind speed. It gives you voltage, but we want to convert that to wind speed. We built it. We building, gilding, sab karke bana diya. The problem is, we didn't have the initial data. How do I know what speed is what voltage? We need to know that, right? So then we went to aeronautical department. In IIT Madras, they had a big wind tunnel, so which can generate speeds from like 5 to 120 kilometers per hour. So we went there, we talked to them, we told them, boss, देखो हमारा ऐसा project है, we need to the wind tunnel and everything. There are other people also. There are 10, 15 people who wanted to use that wind tunnel thing. Then he said, okay, Saturday afternoon, he gave us 2 hours of time. There'll be one person here. He will come. Every 10 minutes, he'll switch on the wind tunnel for 1 minute. So 3 different speeds. He will give 5, 10, 15, 20, 25, 30. He will give 6 speeds. You guys have to measure it. So we went to the wind tunnel. We kept our equipment there. Then he announced, okay, speed is 5. Then we measured the voltage. Speed is 10. We measured the voltage. So we got 6 readings like that. Then we are pretty damn sure like this will be a linear function. So the values came something like this. We didn't even understand what the hell was this. Then what do? We just pushed it little up, pushed it little up. We made it a straight line. We did all nonsense. We did something. And then we finished the project and we went and submitted it. And our teacher was even more awesome. He brought a table fan. And table fan has 3 speeds, one, two, three. And he's like, find the wind speed of this table fan. I said, like, what the hell, yeah? And we kept our project there and he switched on the wind speed and he said, you should not touch it. It should be there only. I said, ठीक है. He switched on the fan at speed 3 and our thing started flying like a helicopter. So like, it was an interesting experience. At least ours didn't break. We did something. They gave score on different things, the cost of the material, uniqueness of the project, how it works well, accuracy and all. So there are 5 different ratings and each rating gets 50 marks. We got some 33. So it's like, ठीक है. Really didn't do that great, but it was fun for a week, running around like mad people. So this was 20 years back. Now I think things are much better. They have more workshops and they have more stuff. Anyways, so let's see how this works actually. So if you have a person here and let's say the whole system is at rest and this guy is 50 kg. This is what the weighing machine does. So you take the person, like I said, it doesn't know what is your mass. The normal reaction, your weight is 500. So it will say, okay, N is 500. And then what it does, it takes the reading. I'm assuming G is 10. N by G, and it will show 50 kg. Yeah, no props. But the same thing, take this guy and put him inside a lift. So take a lift, take the weighing machine, make him stand inside. Now this time, let it accelerate with A is equal to 2 meters per second square. The same guy with the 50 kg weight. Now, if you ask the weighing machine what is the weight, if you draw your FBD, we have the normal reaction. We have your weight 500 and we have the acceleration. The normal reaction will be N minus 500 is equal to 50 into 2. The normal reaction is 600. Now the weighing machine really doesn't care. It will see the reading is 600 and it will say N by G. It will show 60 kg. Are you getting the difference? So weighing machine does not measure your mass. It does not know what you are. So it will simply measure N and it will finish it off. So if someone wants to lose weight, the fastest way to lose weight is get into a lift and let it accelerate downward. You lose weight. You want to gain weight, get into the lift and accelerate upward, you'll gain weight. That is the fastest weight loss program, but temporary. But yeah. Let's see a question on this. So there's one decent question from HCB. Let's do that. There, let's give it a try. The most disastrous project that we did was making a submersible, a small submarine kind of thing, which goes into the water. It has a robotic arm and it's supposed to pick things. It went inside, but never came out. We spent 35,000 on it. Yeah. It had a leak. We knew there was a leak. We didn't know what to do with it. We tried closing it, every material, nothing worked. And since the deadline was coming up, we had to come up with some plan. One of our super senior gave us an idea. He said, like, see, you can't let it, it's going to sink anyway, right? So how long you want it to float? So problem ye tha. We made some weird design. We actually brought this, big PVC pipes, which they use for water piping and everything. We brought two big things. We sealed this thing. Then we mounted the whole steel structure here. We kept some motors here, like a drone kind of thing. So these things were, you can fill the water, remove the water, you can sink it and float it, blah, blah, blah. Problem tha wireless nahi tha. So we had to get a wire from here to outside. When you're keeping a wire here, whenever the wire bends, the hole opens up. No matter what you do, that hole opens up every time. We couldn't seal it. Water always leaks inside. And then we couldn't do anything about it. Then one of our senior told, like, fine, TK, you can't close the hole, but how long do you need this demonstration to work? We said 10 minutes max. If it works for 10 minutes, it is sufficient. Then he said, use diapers. Use diapers. If you can't let it sink, use diapers. I'm the one who went to the shop and I said, give me diapers. I didn't know, but never in my life I brought diapers. He said, like, he gave me chota. I said, give me the biggest ones you have. So I brought that adult diapers. We kept this whole circuit board, with diapers. We sealed it. We did everything. It didn't work, yeah. It sank in 2 minutes. Diapers couldn't handle that flood, I guess. Yeah, well, not a bad idea. Then we had ropes anyway connected. When it is going to sink, na? We pulled it out with ropes. It was done in a swimming pool. So you will have fun. You will learn all stuff. Let's get this thing. 15. Take GS10. Huh? Someone did get it. Right, Ahna. I think he's asking for the weight. Na? He should not give in newtons. First one is asking for the reading. Reading, see, what you measure and what you show are different. You measure normal, but you show mass. Yeah. IIT Madras that's Asia's largest wave pool. They literally have all this small subs and all into it. Anything? What is the answer? Yeah. Let's see the first part. See what he's saying. A mass of 60 kg standing on a light weighing machine. So the machine is kept in a box of 30 kg. So the box ka weight is 30 and this guy ka weight is 60. So total 90. If the man manages to keep the box at rest, So the first case, when the box is at rest. So my suggestion would be take the whole thing as one system. If you take the whole thing as one system, you will see there is a tension here, there is a tension here, and you will see a total weight m plus mg. That this is what you will see. The normal reaction becomes internal. So we get 2t is equal to 900. So we get tension is 450. So this much force is applying to keep the box at rest. Now draw the FBD of the man only. So this is man plus box. Now when you take the man only, the rope is pulling up. You see, if you're catching a rope, it is going to pull you. Your own weight is 600. And the normal reaction is pushing down. Acceleration is zero because anyway you're at rest, and this is 450. This will give you normal reaction 150 newtons, and the reading will be 15 kg. Yeah, taking 9 point here would be a little messy. That's what it will show. Second part of the question, he's saying, with what force should I pull the rope so that the weighing machine will show the correct weight? Now, again, same story. This time, again, we'll take the box and the man. Both are going with the same acceleration. Tension, tension. Your weight 900, and this is your acceleration. 2t minus 900 is equal to total weight 90 kg into acceleration. Now, for the man, if you look at the forces, tension, your own weight 600, and you're saying the reading also shows 60, so n is also 600, and this is the acceleration. So t is equal to 60a. Perfect. Take this, dump it here. This will be 120a minus 900 is equal to 90a. A is equal to 30 meters per second square. Tension is 1800 newton. So you're pulling the rope so hard, the whole system is accelerating up with 3 times the gravity. That is how you do. See, if you want to talk about the weighing machine, you have to separate the man from the weighing machine. If you take the whole thing as a system, the weighing machine always becomes internal force. So you will never get the Denka value. All clear with this? Clear? That's a little about weighing machines. So be careful with that. Weighing machines measure normal reaction, but they show you N by G. This is another good question. There, go through it. Read, read, read. Did you guys get the question? So there is a massless frame. That's an important word. So there are 4 strings. So everything is symmetrical. Gravity is acting. And the 2 things which also have, both have mass m and mass m. If you leave the system at this instant, just after release, what is the acceleration of that frame? Nee, Anish. Don't get confused. Why can't massless systems accelerate? See, F is equal to ma. If m is zero, force can be zero, right? A ka value can be anything. So that's one important statement there. The net force acting on a massless system is zero. Keep that in mind. It doesn't mean it is going with infinite acceleration. Net force and net torque. I know that comes in rotational mechanics, but net force and net torque on a massless system is zero. So torque is for rotations and stuff. So get it. So now if you just look at the FBD of the frame, if you look at the components, tension, right? There'll be tension here, tension here. So that would be, we have T cos theta, we have T sin theta, and we also have T downward. And there are four of them like this. T cos theta will anyway cancel. This will be 4t minus 4t sin theta is mass into acceleration. Mass ka term is zero. Therefore, 4t minus t sin theta is zero. Take out t common, you'll end up with 4 minus 4 sin theta is zero. So t has to be zero. If t is zero, that means both the bodies are falling with g. This is same like that massless pulley thing. Then what? So balls are falling with g. What about this thing? Now, right, Anish, just think about this thing logically. Instead of thinking it is a frame, can you think of like this? Look at this problem. This guy. If you just think about it, this isn't this ring behaving like the frame? The string is passing through the ring, isn't it? The same way, if you look at this picture here, the string is passing through the frame, isn't it? So that means I can use that constraint. So we have one ball here, we have one ball here. So tension. Initially, everything is at rest. And this guy, the tension is T sin theta. And tension is T. And this guy is falling with G. This guy is falling with G. I'll assume this guy is going up with acceleration A. Power method. So T into minus G plus T into minus G plus T sin theta minus T into acceleration must be zero. If initially you had no velocity, if you initially had velocity, this would have been wrong. Initial velocity is zero, so it works out. Technically, you should take for velocities and differentiate. So then you end up with A is equal to 2G by 1 minus sine theta ka minus n, meaning it's not going up, it is also actually coming down. Clear with this? That's your acceleration. So maybe I'll do one thing, I'll take A down only. Okay, minus indicator is just going down. All clear this? So even though your net force is zero, you can still have an acceleration because it's like m into A. If m is zero, A can be anything it wants. So not a tough question, but if you don't have an idea, right, how a massless systems behave, or it can be scary. That's it. But once you know the idea, right, you take a massless system, net force is zero. You'll be able to handle it. Clear with this? Yeah, it's a good question. These are the kind of questions which are not tough. They're a little different. It's not lengthy to solve. Yeah, but you have to think. Next thing, springs. Springs are important, but mostly we will see them a lot in work power energy and later on a chapter called SHM. Here, we really don't deal much because we keep them in equilibrium. We don't make them elongate and stretch and do all that stuff. They won't oscillate. So what does spring do? Basically, they oppose deformation. Springs, they don't like to be compressed. They don't like to be expanded. They oppose deformation. So if you try to compress, it will try to push you back. It will try to elongate, it will pull you back. So they oppose deformation. They generate restoring forces. You heard this word before, internal restoring forces. The word restoring meaning these forces are trying to bring you back to the natural state. They generate restoring forces, which is proportional to elongation or compression, meaning the more you stretch, more the force. It's a linear function. So we represent a spring like this, the curly thing. This we call as natural length, meaning it's neither elongated nor compression. That's called a natural length. So if you take a spring and if you try to compress this, try to pull this, if you stretch it, the spring will pull you back. So you pull the spring, it'll pull you back. You push the spring, it'll push you back. So X can be elongation or compression. The spring will push you back. So if you notice here, the force due to the spring and the X both are always opposite. So force due to the spring is minus K X bar. They are always opposite. What is that K? K is called a spring constant. So K tells you how strong is the spring. If K ka value is very high, that means it's very difficult to stretch the spring. If you ever seen your pen ka spring, right? It's very thin and all. You just pull it, it'll break also. Did you ever see the spring inside a local train? Next time if you ever get a chance, right? Local train ka niche na, just go down a bit and if you see, you'll see a spring. It will have a thickness of, the spring will be thick, as at least 2 times your thumb ka size. It looks like a rod. That spring thickness will be like a rod. And evenings when the train is fully filled, that whole spring gets compressed literally. Getting it? Because our Mumbai local trains, right? They're designed for a capacity of around, I think, 1,200, but almost 4,000 people travel in the train. So there is a word for it. It's called super dense traffic. I think 3 to 4,000 almost. It's a super dense traffic. Only other country which has that kind of traffic is Tokyo, the city. So we have super dense traffic. Like people literally hang. क्या करें ना? It's packed. Yeah, it's dangerous, but then what? Just think about it, logically. Every day you witness world's largest migration and you don't notice it. The total number of people who travel in Mumbai locals, right, is number crosses more than 70 lakhs. 70 lakh people travel from north to south in the morning, and by evening they go back from south to north. That 70 lakh is population of some of the countries in Europe. So it is the world's largest migration happens on daily basis. It's a it's a big thing. We just don't notice it. For you guys, it looks like normal because you're born and brought up here, na? When I came to Mumbai in the beginning, right, 2013, when I came to Mumbai, I was like shocked. Like I was like, what the hell is this? Like in my life, I've never seen so many people. So my mom called up me, and she said, like, Arun, Mumbai mein kya hai? I said, there are a lot of people. She thought I was joking. So when she came, I took her to Bandup station in the evening. Then I said, now see what happens. And luckily, I guess, four trains came at the same time, two slow trains to and fro and fast trains to and fro. People just spilled over, and my mom is like, what? Then I told her, can you see that big green color post? I said, huh, if you get lost, come there, I'll be standing. And she got lost. It was fun. Then I told her, you want to see more people? Let's go to Dadar. Evening, Vasai train. She said, like, no. Interesting. Anyway, so the K is your spring constant. So higher the K, more difficult to deform the spring. So K tells you how difficult it is to deform a spring. Your vehicles have shock absorbers. They're actually made of springs. Right? Shock absorbers are springs. More difficult to deform. So that is the meaning of K. Whenever you think about a spring constant, think about that. Yeah. Next thing, combination of springs. Now for this, how exactly we measure the kk value, we have a separate chapter called elasticity. We will deal there, but for now, let's handle this thing. What happens if we keep springs in series and parallel? So if we keep two springs in series, so two springs are in series when they have same tension. So if you keep two springs, K1 and K2, they will have X1 and X2, they'll have different elongation, but their tension will be same because both are connected to the same joint there. And you want to replace this with one spring. We call this thing K equivalent, just like resistance. So here the tension in the spring is K1 X1 is equal to K2 X2 is equal to K equivalent X equivalent. Means you're saying this one spring should stretch the same amount as these two springs. If you solve this, you will get it 1 by K equivalent is 1 by K1 plus 1 by K2. They will act like opposite of resistors. So when you keep springs in series, actually they become weaker. The overall K ka value drops. So K equivalent is K1, K2 by K1 plus K2. So springs in series are like resistors in parallel. If you keep springs in parallel, they have same elongation. This concept is very important. Later on, we have a chapter called oscillations. We will use this. Will be quite useful there. So if you keep two springs in parallel, K1, K2, and you replace them with one spring. Here they will act like series kind of thing in resistors. So K equivalent is K1 plus K2. So when you keep springs in parallel, they actually become stronger. This is combination of springs. So what happens if you cut a spring? If you cut a spring, the spring constant actually changes. Now the formula for K, later on we will see it. So if you have a spring, the formula for K is given by YA by L. So this Y is called the Young's modulus. It depends on the nature of the material. So if you make a steel spring and a plastic spring, steel spring is more stronger. It's called Young's modulus. So you can think of it as the strength of the material. So if you take Y steel, which is greater than Y plastic. So a steel spring is definitely stronger than a plastic string. So that Y depends on the material. A is this one, the area of cross section of the wire. How thick is the wire? So if you use a thick wire to make a spring and a thin wire to make a spring, the thick wire will be more stronger. L is your length of the spring. So when you're cutting a spring, Y will not change, area will not change, right? So K into L is Y into A is constant. How we got that formula, we will see in a different chapter, but for now, you need to know. So K into L is constant. So when you cut a spring, the spring constant actually increases. And there is a logic also, think about it. Imagine you have a long spring, okay? Let's say there are 100 turns. If I stretch this spring by 1 meter, that means every turn here is expanding by 1 centimeter, isn't it? But if I take a spring with only 10 turns, and if I try to stretch it by 1 meter, each material has to stretch by 10 centimeter. The material is getting more stretched. And when you stretch it more, you get more tension. So, so a long spring will have what you call less tension there. So this is how you change the spring constant. K into L is constant. So if you have a spring, and if you decide to cut it here, let's say इसका length is L1, इसका length is L2, then this will have its own spring constant K1, this will be K2. So using the formula, this will become two pieces. K1, L1, K2, L2. K1, L1 is equal to K2, L2 is equal to K into L. The product remains same. Example. We have a K and L. Let's say this is cut into L by 3 and 2L by 3. The smaller spring will have K1 L by 3, K2 2L by 3. So K1 L by 3 is K into L. K1 is 3K. It becomes 3 times more difficult. K2 2L by 3 is K into L, which is 3K by 2. So if you cut a spring, spring constant changes. So keep this in mind. Yeah, cutting of spring is like a reverse of resistor. So, but clear with this? So when you cut it, length decreases and K increases. The spring will oppose you more if meaning a smaller spring and a bigger spring made of same material and same wire. The smaller spring is more difficult to stretch. All clear with this? Got this? So that's the main idea there about combination of springs. Let's see a few questions on this. So we have M here. Let's say this is 3K, this is 3K, this is 3K, this is 2K, this is 2K, and this is K. Let this point be A and let this point be B. So the system is released slowly from natural length to equilibrium. I mean, you just didn't leave it, okay? It's not oscillating. The system is released slowly from natural length to equilibrium. Find displacement of the block and point A and B. You're getting it? Someone is holding the block and they're gently leaving it. So meaning system, it will become like this. It'll stretch, it'll stretch, it'll stretch, it'll stretch, it'll stretch. The block ऐसे नीचे चला जाएगा. So how much did the block go? How much did B go? How much did A go? So we'll not be handling all that oscillation and jumping things here. Answer, there will be a K inside. First, find the elongation of the block. First, find K equivalent. Like you can replace the whole thing with one spring actually. Try whatever you can. I'll give you a minute or two and I'll show you. Okay, for one big number. Anyone else? That's right. Yukti. Get the remaining two. Displacement of A and B also. Okay, let's see. Let's ABCD, right? So if you look at the three springs here, all three are in parallel. In parallel, what you do? K1 plus K2 plus K3. You just add them up. So I can replace this guy with one spring, 339K. Then I can replace 2K, 2K with one spring, 4K. And then I can replace with one spring, K. Great. And what is the K equivalent? Now all of them are in series. So 1 by K equivalent is 1 by 9K plus 1 by 4K plus 1 by K. Perfect. I don't need this actually, but yeah, the K equivalent looks interesting. Nothing much we can do it. So that would be 5 by 4, 49 by 36K. So that means you can replace all these three springs with one spring of 36 by 49K. That means we can simply say K equivalent into X is equal to mg. So 49 mg by 36K. This is the distance moved by the block. Right? The total elongation in all the springs is equal to this. But like I said, you don't need to do this. You can do this even better. So if you take this point is A, so let's say this spring is stretching by x1. This is B. Let's say this spring is x2. So can I say like this? So displacement of A is the elongation in 9K spring. Whatever elongation happens in 9K, that is only responsible for A to come down, isn't it? No matter how much these guys stretch, A will never get affected. So elongation in 9K is the displacement in A. And what's the tension in all the springs? Tension in all the springs is mg because all are in series. Tension in all springs is mg. So this would be simply mg by 9K. What's the displacement of B then? Displacement of B is elongation in 9K and 4K. Because whatever 9K and 4K stretch, and how much is that? Mg by 9K plus mg by 4K. That's what I said. You need not even find K equivalent. Then you'll argue what is elongation in K? Elongation in 9K, 4K, K. Then you get mg by K. So if you see, that's how we got 1 by K equivalent. You can literally find elongation in each spring and just add up all of them. So this whole setup will look like one big spring of 36K by 49. Clear with this, everyone? Any doubts on this? Next up. Let's say we have a spring balance. Find the reading of the spring balance. I'll give you one more bit. There are four kind of systems here. So what does the spring balance do? The same way what a weighing machine does. They don't measure weight. The spring balance measures the tension in the string, and it shows tension by G. So you need to understand machines, they don't actually show what they measure most of the times. Spring balance measures tension in the string. So indirectly, I'm asking you, you can replace the spring balance with a string and find the tension. And it shows whatever is the tension, it will divide by G. Just like your weighing machine. Let's get this. Simple question. A decent means or a CD level question this is. The four different questions. Get the answers. Let's see. Let's see. This thing is all about finding tension. So what is the first? The tension. I keep telling you how to find the tension. Cut it. You want to find tension. So this will be T. This will be 100. So tension is 100 Newton. So the reading will be 10 kg. Even though there looks like two blocks here also tension is 100. Tension is 100. So even this will show 10 kg. This is that a horse car example. Whether you pull one side or you tie it to a wall, it's the same story. On the other hand, this is easy here. So this guy will show the tension here. T1, this is 50 newtons. This guy ka tension T2 will be the total weight, 150 newtons. So this spring will show 15 kg and this spring will show 5 kg. Yeah, this would be an interesting one. So this is tension. So the spring balance is massless, so tension will be same on both the sides. This would be 100. This would be 50. This is actually accelerating. So if you calculate this, you will end up with t minus 50 is equal to 5a, and this will be 100 minus t is equal to 10a. Yeah, add them, and you end up with 100 minus 50. You can do the net pulling force method to get acceleration. So 100 minus 50 by 15, 50 by 15, that's 10 by 3. And we end up with tension is equal to 200 by 3. So the reading will be 20 by 3 kgs. The third one will be a good question. System is not at rest. It won't show 10, it won't show 5. It will show the tension in the string. So, and the system is accelerating. So that, yeah, the C1 is still a good one at a means level. All clear with this? Take a break. Come back by 9:48. We'll continue from here. Any doubt so far? Chalo, come back by 9:48 then. Come on, everyone. Let's start off. Comes on, everyone. So we got a spring between two walls, K and L. Somewhere at this point, right, on the spring, someone connected a rod. Let's call this point. And you started pulling this with force F. This distance is point to L. You're not pulling the end of the spring, you're catching at the middle of the spring and you're pulling it. And this is point at L. So at point A on the spring, force F is applied. Other scans on. Find the distance moved by this point A till equilibrium. You're applying force at the middle of a spring, not exactly middle, point to L, and you're pulling to the right side. So spring will compress and it comes to equilibrium. So how much distance did A move? I mean, if you just think about it, right, the right side of the spring, this part is getting compressed and this part is getting elongated. So the whole spring doesn't have same elongation and compression. So this is a little different. Give it a try. How do we do this? Any answers? Let's see. You cannot use F is equal to kx directly here because the whole spring is not identical anymore. You have messed it up. By pulling it in the middle, you made one part of the spring compress and the other elongate. So what do we do? See, the whole question, it is there only. You started pulling at the middle, and that pulling in the middle created the whole problem. The right became something else, left became something else. When you put it like this, right, it is clearly telling you, boss, separate the problem then. If your problem was that right is doing something else and left is doing something else, then just cut it there. So that's what is thinking, like, when you ask questions to yourself, right, the problem was that right and the left are behaving differently. But it also means the whole right thing is behaving as one and the whole left thing is behaving as one. So just split them as K1 and K2. 0.12 and 0.8L. So it has become like two different springs. And we know K into L is constant. So this has become the cutting of spring ka thing. So K1 into 0.8L is equal to KL. K1 is 5K by 4. K2 into 0.12 is KL. K2 is 5K. Right? So the whole problem looks like this. We will just imagine A is an imaginary block. Two springs like this. Someone pulled with force F, and let's say this thing moved by X. Now, if you draw the FBD of this block, what are the forces acting on this block? We have force F. The right side is getting compressed, so it will push back, which is K2X. The left is getting elongated, so it will pull back, K1X. So that is the thing. The right part gets compressed, so it will push you back, and the left part is getting elongated. It will pull you back. So both the forces will be in the same direction. But they're not exerting same force. The right part is compressed, and the left is elongated. The distance moved by this imaginary block A is the distance moved by that point. Anyway, the mass never mattered. Yeah, then you're done. So F is equal to K1 plus K2X. So that is 5K by 4 plus 5KX. X is equal to 4F by 25K. Is that making sense? Since the right and the left are different, then just let's cut it there and treat them as two different springs. But the moment you cut the spring constant will change. So get the new spring constants and done. Now the whole question has become like this. We have two different strings with a block in between. Clear? That is one. Next thing. So massless springs. Now, most of the springs that we study, right, are all massless. But if a spring has mass, it actually behaves a little differently. So let's see what is the difference. So in a massless spring, you have a block M, and if you got a spring here, and let's say this was your natural length. Initially, it would have elongated a bit because of the weight. Now, the moment you cut here at the top or anywhere else, the moment you cut, the spring, right, will suddenly drop here. Instantaneously, it will come to the natural length. Because the spring force, there's a kx, there's no mass, you get an infinite acceleration there. Basically, so kx is equal to ma. So force is not zero, but m is zero. Now a has no option, like, right? So a has to become infinity. So what it means is the spring will suddenly come to the natural length. The tension suddenly becomes zero. Yeah, looks weird, but massless springs don't exist in nature. It is also a hypothetical concept. So when a massless spring is cut, it immediately comes to natural length. There is no time delay. So the moment you come to the natural length, that means your tension has become zero. The moment the tension becomes zero, this block will start freely falling. So it will just fall down with G. There is no delay. But what if springs have some mass? Previous working here, Karthik. Clear? What if springs have mass? If springs have mass, now the moment you cut, because the spring has some mass, it takes time. You will not have infinite acceleration. There will be some finite acceleration, large, but there will be still some time. So let me show you how it looks. So when a spring is cut, it takes time for the spring to come to natural length. This is how real life springs behave actually. Let's say this is how it looks. Let's say this is the natural length. No, you're cutting it here. The moment you cut, this block still remains at the same place. Huh? That's the thing. This block doesn't move only because still there's a kx which is pulling it up. Acceleration is still zero. If you give a little more time, this will come till here. The block is still here. The block doesn't move. Then the moment the spring comes to the natural length, now it starts moving. At this point, you have come to the natural length. Now the spring force has become zero. Now your acceleration is g. At this point, the spring will remain in natural length. The spring will still remain in, because now there is nothing to elongate it. You cannot have tension there. And the whole system falls with g. So there is a delay there. So the block does not move till the spring comes to natural length. Because as long as there's elongation on the spring, it applies kx force. So basically the force transmits, it takes time. The tension in the spring itself is changing. It's a little difficult to study the whole thing. That's why we take massless springs. Block does not move till spring comes to natural length. And this is how real life springs work. Yeah, but until unless they mention, always assume springs are massless. Just keep that in mind. This is how it would look. Why are you not? Just yeah. Able to hear me also? Wait, kept it on mute. Okay, yeah. You're not able to see the screen, yeah? Let me just share it. Now, can you see? There is some problem with this. What did I do? ठीक है, something is happening. I'm not sure what happened. That was a good video to see. Okay, holes. Yeah, something happened to my PC only. It crashed. ठीक है. Great. Let's see a question in the meantime. I'll try to figure it out. Maybe I'll show you today or next class. So that's one thing about the spring. So if you have a massless spring, the moment you cut it, you just come to natural length. But if you have a spring with a mass, it would take some time. But what happens with strings? This is important. Unlike a spring, right? Strings also, they react instantaneously. Tension in the string can change instantaneously. Because in a spring, right, the force is k into x. If your elongation is, as long as your elongation is x, the spring force is kx. It doesn't matter how much force you apply. The tension in the string can change instantaneously. Whereas in springs, it takes time. Let me show you what it means. For example, let's say you have a string and you have a block of muscle. And let's say there is a hook here and we are trying to attach one more block M here. See what happens. Initially, tension was T and we get T is equal to mg. The moment you attach this block with a hook, the tension suddenly becomes T dash and T dash becomes 2 mg. It changes instantaneously. So strings, right? They can change the value of tension suddenly. But imagine you do the same thing with a spring. Let's say we keep a block here of mass m. So this is pulling with kx. That's your tension there. So kx is equal to mg. Now, the moment you attach a block, the elongation is still same. The spring doesn't care how much mass is there. Spring will ask only one question: what was my elongation? As long as my elongation is same, I don't care. I'll apply the same force mg. The system will accelerate though. That's a different story. The spring forces don't change immediately. They take time. Because spring force depends on what is my elongation and compression, and they would take time. It will take time for the blocks to come down, the spring to elongate and everything. So keep this in mind. So spring forces cannot change suddenly. They take time. Yeah, if you give little time, then they would also change. But for a string, you don't need time. They take time to change. So is this clear, everyone? Great. Let's see a question on this. These are one good set of questions. Let's say this is M, this is 2M. This is point A and this is point B. Massless springs, system is at rest. Find acceleration of the blocks. Just after cutting, case 1, you're cutting at A. Case 2, you're cutting at B. Two different questions. Think how will you do this thing. Take a minute, then I'll show you some steps and then we'll see more. Manav, do keep your cam on. How do we handle this? So listen to the steps. Step 1, find the tension in the springs. Step 2, the springs which are cut, the tension becomes 0. Whichever spring you cut, that tension will become instantaneously 0. The other ones will not change. Spring which is cut has 0 tension. Other springs are unaffected. Step 3, apply F is equal to MA and solve. Okay, so let's see how to do this. Step 1, let's find the tensions. Initially, system is at rest. So you can clearly see here. So this thing will be tension at B, that is only balancing 2 mg. This is tension at A. This is balancing the total weight 3 mg. I hope that was okay, clear, right? The upper spring is balancing 2 blocks and the lower spring is balancing 1 block. Then the first part, you're cutting at A. The moment you cut at A, the tension at A becomes 0. What about tension at B? Tension at B will still remain same, 2 mg, because the spring 2 does not know what happened with spring 1. Yeah, if you give little time, then A will move, then the spring B will compress, and then all things will happen. But the question is instantaneously. Draw the free body diagram. For block M, the free body diagram will be TA, which has become 0. Your own weight is mg. The TB is pulling down, that's the spring force, which is 2 mg. This will give an acceleration of 3g. Total force 3 mg. If you look at B, this will be tension TB, which is 2 mg. Your block weight is also 2 mg. This acceleration will be 0. Meaning at that instant, 2m will think nothing changed. Whatever happened at A, it remains there only. Like 2m does not even know something happened at A. Give little time. If you give little time, then A will move down, then the spring will compress, and then 2m will fall. But they'll always ask you questions just after cutting. Because how much it will move, how much it will change, it becomes a mess to calculate. So look at the B part. Now you're cutting at B, so TB guy becomes 0. TA guy does not know something happened with B, so the tension will remain same. Draw your free body diagram. Tension at A, your own weight mg and TB has gone. And this is 3 mg. So 3 mg minus mg, you will go up with 2g. Whereas for 2m, TB has become suddenly 0. Your own weight is 2 mg. 2 mg is equal to 2 ma. You'll fall down with g. Is that making sense, everyone? Clear? Easy. So find your initial tensions. Whichever you're cutting, make that 0 and everyone else will remain same. And then draw a new FBD and finish it off. Let's see one more. So this is one set of problems, cutting off springs. They just cut it and they'll ask you. This is A, this is B, this is C. Actually, it doesn't matter where you cut it. In a massless spring, you cut anywhere, it will become 0. Same story. Find the acceleration of the blocks just after cutting at A, B, C. 3 different questions, 3 different blocks, so total 9 answers. And this will cover most of the cases. And be careful, A is a string, not a spring. Strings behave differently from springs. So there, give it a try. Anyone not clear with the question, please ask me. Let's see the first thing. Step one, find the tension in the springs. We follow the process. This process thing which I keep saying, I actually got inspired, by coding. If you see when you write a coding, right, you make an algorithm, isn't it? How do you make an algo? How do you teach a computer how to think? You make a process. You just can't expect it to do different things. So there's an algorithm for everything. The way you live your life, it's an algo. Maybe you don't realize it, but there is a way. Morning you wake up, you go to the washroom, you brush with your right hand, you brush in a certain pattern. It's all in your mind. Habits. So these are kind of algos. The only way you can break them or make them better is if you understand how it works, and then you keep changing the process. Solving questions is no different. If you think every question is different, you will get overwhelmed. There will be always exceptions, but the thing is, have a process, and when things change, understand where they're getting diverted. That helps. Without a process, then everything will look weird only. So let's find the tensions here. Let's start from here. This TC guy is balancing 3 mg. Tension at B is balancing 2m and 3m total weight. So anyone is confused about these tensions, please ask me. 5 mg. If this is TB, this is also TB, which is 5 mg. This block ka weight is mg, so TA is 4 mg. Great. These are the initial tensions. Perfect. Let's start from cutting at A. You're cutting at A, tension at A becomes 0. TB will say, I have no idea what happened. I will remain same. TC will say, I will remain same. The other guys don't care. Then we'll draw the free body diagram. So A ka FBD, TB is pulling up. That's your 5 mg. That still remains same because it is connected to the spring. Your own weight mg. Perfect. And your mass is m. So you will go up with 5 mg minus mg by m. You go up with 4g. The 2m block does not even know what happened. Basically, the springs, right? They're like shock absorbers. Whatever happened on the other side, they are delayed. They will take time for them to react. 3m. So this guy will think nothing happened. Acceleration is 0. Same thing if you talk about 3m, even it will say, boss, nothing happened. So 2m and m even does not know what happened there instantaneously. This is inertia. We keep saying it, inertia, inertia. What is inertia? This only. They will keep doing whatever they're doing until unless something happens. So at this instant, nothing changed. So this is what will happen to A. What about B? Now here you have to be careful. When you're cutting at B, what is the tension at A? We don't know. That is the answer. Because the tension in the strings can change instantaneously, there is no guarantee it will remain the same value. If you're cutting at A, that is great. But if you're not cutting at A, the way you're confident about a spring, you can't be confident about a string. Tension in the string can change. Yeah, if it remains, that's a different story, but it can change. So the answer is you don't know. Can change. So we are not sure about the previous value. So what is the tension at A? We don't know. Okay, let's try to figure it out. Tension at B, that became 0, I'm sure. Tension at C, that didn't change. Great. Great. Let's start with A. So we draw the FBD block TM and your TB becomes 0. I think I can do it in the next page. This TB became 0. You have mg. Now something interesting happens. Strings cannot push. The moment the TB becomes 0, there is a string at the bottom. The string cannot sustain this. So TA also becomes a 0 because it becomes loose, and this block falls down with G. Is that making sense? The moment the TB becomes 0, the block has a tendency to come down. If it tries to come down, string is not going to fight back. String will immediately tension becomes 0 and you're gone. Strings cannot push. The string becomes loose and M will fall with G. If you look at 2M, TB became 0, your own weight 2mg, and TA is 3mg. Yeah, and this net force will be 5mg by 2, 5g by 2. Whereas for 3M, the tension at C is still 3mg, your own weight is 3mg. Yeah, this guy is at rest. Please have a look at this. So you have to be careful about the strings. If you see in the steps also, na, I said springs which are cut have 0 tension, other springs are unaffected. I never talked about strings. So strings, we don't know what happens. So that is the thing. You should not be sure about it. You have to prove. Then let's cut at C. Yeah, this is how they can play around. Like, so if you're cutting at C, tension at A, I still don't know. Tension at B, that will be 5mg. Tension at C, that becomes 0. Perfect. Now let's look at M. Tension at B is 5mg, which is definitely greater than mg. TA. Acceleration is 0. Why? Because the string cannot stretch. The bottom string cannot stretch, so it cannot move. Therefore, acceleration is 0. Therefore, tension at A is 4mg. So whatever extra tension you need, it comes from here. But anyway, it doesn't matter. For a B, TB is 5mg. Your acceleration is 2mg. TC has become 0, and this acceleration will be 3g by 2. Whereas for C, TC became 0. Your own weight is 3mg, and yeah, you're falling down with G. Clear this? And that's how strings behave when you cut. Is that making sense, everyone? Have a look at this. Ask me if you're confused about it. Let's hope this works. Maybe something is going wrong with the Zoom only. You guys are able to see the screen? You're able to see the screen, right? Okay. Yes. Able to hear the audio also? Okay, now can you hear me, right? Yeah, this thing, volume is resounding actually. Okay. Now you can hear me. Look at that spring there, huh? He's leaving. There's a big spring there. When he leaves it, see what happens. The upper part is falling. Look at the bottom part. It doesn't move at all. The upper one is coming. The lower still doesn't move. The lower part doesn't even feel something is happening at the bottom, top. You will see this in another view. If you see this from the bottom view, look at this. This is from the bottom view. Same thing. The upper one is coming down. The lower one doesn't even react. And this is how springs with mass behave. Massless spring would be instant, it'll just close. Now it moves. Clear with that? There, that's a bit about it. So when we catch up on Wednesday, we'll continue from here. We're almost